Hello. In this video, we'll be looking at examples of center of mass in one-dimensional system. So let's recall first the formula for the center of mass. It's equal to moment of mass of the system divided by the total mass. So moment of mass of the system is simply the sum of all the moments. So the sum of the moment of all the particles in the system. So say for example we have n particles. The first particle has mass m sub 1 located at x1, while the second particle has mass m sub 2 located at x sub 2 plus, and so on up to the nth particle, m sub n x sub n. So this is the moment of mass of the system, while this one is the moment of mass of the nth particle divided by the total mass, which is just the sum of all the particles. So n particles. That's it. So that's the formula of the center of mass. Now let's look at this example. Find the center of mass of a system composed of three objects with masses 3 kilograms, 2 kilograms, and 4 kilograms, and located at the following points on the x-axis, say for example. So let me say this is negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, and 3. So meaning here are the particles. The first particle is located at x equal to negative 6. The weight is 3 kilograms. Next, at x equal to 1, here the mass is 2 kilograms. And lastly, at 3, here the mass of the particle is 4 kilograms. Find the center of mass. So the center of mass is equal to the moment of the first particle. So we have 3 times negative 6 plus the moment of the next particle, which is 2 kilograms times 1 unit, plus the third particle, which is 4 kilograms times its distance, directed distance, which is 3, divided by the total mass, which is 3 plus 2 plus 4. So simplifying, we have here negative 18 plus 2 plus 12 divided by 9. So this. So negative 4 over 9 x bar units. So the center of mass is at negative 4, 9. So it's somewhere here, this point. So the system will balance if you place the fulcrum here. Alright, let's look at another example. A uniform and massless seesaw is 10 meters long, and its fulcrum located at the center. So let me draw an illustration here. So say this is at the center, 0. So meaning the fulcrum of the seesaw is here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is how long our seesaw. Let me remove this part here. And this part here too. Okay. This is our seesaw. A 30 kilogram child here sits 2 meters from the left end of the seesaw. From -5, 2 meters from that point, there is a child seated. Let me draw a child here. Oopsie. Okay. And the weight of this child is 30 kilograms. Next, a 20 kilogram child sits 2 meters to the right of the fulcrum. So from the fulcrum, we have another child here. The weight is 20 kilograms. So the location of this child here is at -3, while this other child is 2. Now the question is, how far from the fulcrum should a 40 kilogram child sit so that the seesaw remains in equilibrium? So let us recall that a system is in equilibrium if the moment of mass is 0. So take note that we have 3 particles or 3 children here. So its moment of mass is given by the mass of the first child. The mass of the first child, which is 30, times its directed distance -3, plus the second child, the mass is 20. It is located at 2 meters from the right of the fulcrum. And there's another child. The mass is 40, but we do not know its location, so that the moment of mass is 0. So let me write that here. Actually, what we have here is moment of mass equal to 0 to ensure that the seesaw is in equilibrium. Now, this is, let us solve. This is -90 plus 40 plus 40x equal to 0. So 4x is equal to, we have a -50 here, moving that to the right side of the equation, we have 50. So x is equal to 50 over 40, or this is just 5/4 meters, or this is equal to 1 and 1/4 meters. So the third child must be located at 1 and 1/4 to ensure that the seesaw is in equilibrium. Okay. So that's it. So to answer the question, how far from the fulcrum, the child must be 1 and 1/4 meter from the fulcrum. So that's it. I hope this video helps in preparation for FA3 and our long test. Good night.